Morning student of class 12th. Today we'll do the nomenclature of anionic species. Okay, today we'll do the nomenclature of anionic species, means to say such kind of coordination compound in which the counterion will comes first and then coordinate entity. Okay, in the previous lecture we discussed that such kind of coordination compound in which the counterion is at the back of the coordinate entity, but now we are discussing the counterion at the front of the coordinate entity, and such kind of coordination compound is known as anionic species, in which when we are removing this Na3, that is sodium ion, from this coordination compound or coordinate entity, the coordinate entity will acquire negatively charged. Okay, so that's why this anionic species is having negative charge, and this is called anionic species of coordination compound. And this is the part 1 lecture for anionic species. Okay, in this case such kind of example, at the front of the coordinate entity there is a metal, that is Na, and inside the coordinate entity this is also a single metal, but always this inside metal is also known as central metal atom. Okay, so this is the coordinate entity we know very well. This is the counterion, and this counterion will be as a positively charged, acquires a positive charge, and this coordinate entity acquires a negative charge. First of all, we discuss a little thing before the beginning of nomenclature of this anionic species of coordination compound. In the case for name of central atom, in the case of anionic species, we use the word -ate in the end of the CMA. That is, suppose that for the naming of the cobalt we will use cobaltate. At the instead of cobalt we are using chromium, so it will be named as a chromate. At the end of the name ate will be added. In the case of Fe we will use ferrate. Okay, in the case of silver, that is symbolized by Ag, argentate. Okay, in the case of cobaltate, this. Okay, so this is an example for the nomenclature. Okay, first of all we will write the name of the front counterion. Okay, now write here sodium, but keep in your mind always we will not disclose or we can say not write the numbering of front counterion. Okay, we will not writing here trisodium, we will write only the sodium. Clear? Similarly, in the case of cationic species, we are not writing the counting of the counterion. Suppose that here Cl3 will be present, we will not write trichlorine, we will write only chloride. Clear? So in the case of this anionic species, in the front of the coordinate entity there is a counter ion which is positively charged. We will not explain, we can say we cannot write the counting of the species of counter ion. Then we will start to the coordinate entity. Similarly, as in the case of cationic species, the number of the ligand hexa. Then we will write the name of the ligand nitrito. It ends with the O. Always negative ligands end with O. Okay, nitrito, and N indicates the donor side of this NO2 is nitrogen. Then we will use cobaltate from this side, cobaltate, and this is the oxidation number, 3rd. Clear? So another example for that. In the case of anionic species, we will not write the numbering of counterion. We will write only the name of the counterion, like that. Potassium. Clear? This is the central metal atom. This is the ligand. This is the oxalate. Okay. So we will write here the name of the ligand with the numbering, that is trioxalate. Here 3 oxalates are used here, but we write here not oxalate. We will write here oxalato. Okay. O comes in the end of the negative ligands, and then ferrate, Ate at the last, and the oxidation number, that is 3rd. In the case of K4NiCN4, potassium tetracyanide, just focus on this one. We are not writing a cyanide, just cyano. We will write here cyanido, clear? And then nickelate with oxidation number of the central metal atom is 0. Okay, I hope this is the, you can understand these things. Okay, thank you class.